Lock up the vote. Done. See how you did. See how you did. See how you did. Okay, so this is actually not an easy question unless you know it ahead of time, and we did not tell you this one ahead of time, so it's a challenge for you. The famous history of this problem is Galileo noticed that the period of the pendulum was independent of the amplitude for small amplitudes, and this is why they use clocks to measure time. So if you just keep the beat here, 1, 2, 3, and then I do a much smaller one, 1, 2, 3, bump in the beat, and we keep the beat, and the beat doesn't depend on the amplitude. If it's small or it's big, the beat is the same. Okay, so that's for small amplitudes. You get that the period is independent of the amplitude. And where does that come from? Is that for small amplitudes, you have the approximation that sine theta is equal to theta. You have this differential equation, which is the harmonic oscillator equation, which is a linear equation. And if you take a solution of a linear equation and multiply it by constant, you have the same solution. So that means the time course is the same, it's just the amplitude is different. So for linear differential equations, the period or frequency is independent of amplitude. And for small amplitudes, this has a linear differential equation. Now once you get to a point where you can't make the approximation that sine theta equals theta, this becomes a nonlinear differential equation. You don't know how to solve it with pencil and paper unless you know elliptic integrals and things like that. But you can solve it on the computer. And the question is, when you do the computer solution, is this the same, faster, or slower? Now you might think it's faster because it's got gravity pointing way down there. But how can you know intuitively that it's slower? Is you replace this pendulum with a different one, which I don't have in stock here. But let's just say it's where you replace this string with a stick. And if you have a stick, then you can have compression as well as tension, and we can look at large amplitudes. So presumably, if this thing goes faster or slower, it's going to get more faster or more slower as the amplitude gets big. So if you take this all the way up to where it almost gets vertical, it's clear, almost vertical, it gets very slow. And in fact, when it gets closer and closer to vertical, the period goes to infinity. So whatever the period is here, it goes to infinity when the amplitude gets up to pi. So assuming that the period is a monotonic function of the amplitude, then you see that the period gets bigger as the amplitude gets bigger. So the correct answer, which most of you got for a change, is B. Now, if you doubt that, how are you going to figure that out without pencil and paper or something? You're not going to figure it out. You just do the experiment on the computer. And at this point, you should all be able to, on your own, without looking up anything, no sample code, nothing, you should all be able to do this on the computer. You should sit down, and if you're not totally fresh on it, maybe it'll take you an hour, but within an hour, every single one of you should be able to answer this question competently on the computer on your own, without copying code, without looking at samples, without looking at things on the internet and so on your own. So if you can't do that, make sure that you do this or some equivalent assignment by yourself. Okay, any questions about this? Yes?
So, I chose D because you said that for small angle data, A is true.
Okay, now this gets to be the hair on the angels on the pin kind of argument. So if we look at the period as a function of the amplitude, and we look at the case where we have the linear pendulum, where the period is independent of the amplitude. So here we have this period independent of amplitude, and it's 2 pi over L over G or whatever it is. So this is the linear pendulum. And then we look at the nonlinear pendulum, and when the amplitude gets up to pi, the period goes to infinity, and this comes down and it approaches like this. So now we have a question, does this ever equal this? So for any motion other than 0, they do not equal. they're asymptotically, the ratio of the two goes to 1, but they're not equal to each other. So then we have a long philosophical argument about whether, well, in the limit they're equal. Does that mean that it depends on whether we're at the limit or not, or so on? So if you wanted to argue for partial credit, I would accept that. Okay, so does this graph make it the linear pendulum, and this is the nonlinear pendulum, which is the one that we have over here. This is theta double dot is equal to minus g over L sine theta, and this is theta double dot equals g over L minus g over L theta. Does that address your issue at any rate? Any other questions or comments? Okay. So now we want to talk about rotation. And let me tell you where we are in the class in terms of the overall structure of the course and where we're going. We started out with a particle in one dimension, spent a lot of time on it. Then two particles in one dimension. Then constrained particles in one dimension, like with pulleys. Then rigid objects moving in a one-dimensional way, like the braked car problem. We didn't spend a lot of time on that. But all of a sudden, when we got to rigid objects, we really had to worry about angular-momentum balance in a serious way. Even though the objects were not rotating, we still had to worry about angular-momentum balance. Now we'd like to take rigid objects, two-dimensional rigid objects, and have them move in more general ways. Before we get to more general ways, let's take a special way which is different from moving in a straight line, which is moving in circles. Now we already did a particle moving in circles. Now we'd like to do a collection of particles moving in circles. And the subject changes a little bit because this is not just going to be independent particles moving in independent circles. They're all going to move together. And we have a new concept which is called rotation, which is a little bit different from this angle theta which we have in polar coordinates. So the concept is we have some rigid object, has some shape. So here's a rigid object. And then we go through this process, which we'll call rotation. And what happens is that rigid object rotates. Now, if we had some reference line here, we could draw a reference line here, and we could call this theta equals the angle of rotation. If we drew some other reference line, say connecting any 2 points in here, we could draw this. We could connect these 2 points, A and B, and we could call this the position of B relative to A, and this is in the reference configuration. Then we can look at the vector from A to B in the after it's rotated, so that's B relative to A. Afterwards, and what if we compare this line to that line? So we have here still our B with respect to A reference. That what we see is that this angle here is also theta. So if you draw any line segment on the object and look at what happens to that line segment in this process we call rotation, then it rotates the same as every other line segment. So all line segments have the same angle of rotation. And we call this kind of rotation a rigid rotation. Is different, say, from the rotation you see if you look in a vortex and you see all these particles going in circles, but they're going in circles at different angular rates, and this is not true. If you drew a little sketch by drawing some red atoms in a little vortex, that sketch would not preserve its shape in that kind of rotation. Here we have a rigid rotation where shapes, angles, distances are all preserved. Shapes, angles, distances all preserved. So our main object of interest today is if we're given some vector connecting 2 points on a rigid object before the rotation, we'd like to know what that vector is after the rotation. Now we already know pictorially how to get that vector. We draw this vector. Then after we draw it, we make a stick. We anchor the stick here and we rotate it at an angle theta and we look at what vector we get, and that's the answer. But we'd like to calculate with that. And so the calculation we'd like to do is, given the coordinates of this vector, the components, the x and y components of the vector, find the x and y components of this vector. So this is, in a sense, a high school geometry problem. It's certainly in Math 294. You've done this in Math 294, is that correct? Who's taking Math 294? Have you done this in 294 already? That's odd. Who took 294 before? Did you think you saw this in Math 294? Raise your hand. Okay. Now, do you think the others saw it too? And they don't remember? Okay, let's do a little quiz question. You take 294 before? Did you do eigenvectors in Math 294? Okay. And now your honesty is established. Okay, well, this is something they should do in Math 294. So this is something we want to work out. Now, when you see these arrows here, one of the representations of these arrows is with two numbers, which is the components. One of the components is the difference between the x-coordinate of the tip relative to the tail and the difference of the y-component of the tip with respect to the tail. That is, you can represent a vector as a point on the plane, and the point on the plane has x and y components, which are the x and y components of the tip relative to the tail. So we can think of this problem that I have on the left as being replaced with this problem. I'm going to take a fixed x and y coordinate system, and I'm going to associate that with unit vectors I and j. And I'm going to look at some point over here. And this point, I can think of this as being a vector. And this is some typical vector. Maybe it's representing this vector here, or some other vector connecting 2 points before the rotation. So this thing has components, which I can call x and y. And this is the position vector. Now, we're going to be taking this picture and rotating it. And we want to distinguish the original picture from the rotated picture. So let's call this in the reference configuration, where we start. And everything in this picture we label with the superscript REF, meaning this is a situation in the reference configuration. And we're going to be keeping track of this point. And if you like, we're looking at the position of this point relative to the origin, but you could think of it as looking at any point relative to any other reference point. The math is the same. Now we're going to take this picture and rotate it. And when we rotate it, we're going to have a new x-axis, a new y-axis, a new I vector, a new j vector, and a new point up here, which has new coordinates. So this is now the same picture rotated. And when we take any object like this, we can imagine drawing a coordinate system on it. And when the object rotates, some coordinate system on the object rotates with it. Now we have to label all these things. This is no longer the x-axis. It's the x-prime axis, we'll call it. This is the y-prime axis. This is no longer the unit vector I, it's I-prime. This is no longer the unit vector j, it's j-prime. This is no longer the r reference, it's the r. And this is the x-prime coordinate and the y-prime coordinate after the rotation. So here's before rotation. And this is after rotation. Now, what's the relationship between x prime and x ref? Those are two numbers, right? 3 feet and 5 feet, or 2 meters and 2 meters, or 6 centimeters and 7 centimeters. Or what's the relationship of those two numbers to each other? Okay, someone want to offer an opinion? Somebody said something out loud? Go for it. They're the same. So what we're saying is we're taking this whole picture and rotating it, and then according to what we wrote over here, all shapes, angles, and distance are all preserved. So this distance is preserved. So x prime is equal to x ref, and y prime is equal to y ref. So what's the question? Well, the question we'd like to address is what happens to the new value of x and the new value of y. So our big question is x is equal to question mark, y is equal to question mark. So we'd like formulas for that. Little teaching issue. Do you get lost in the chaos of the blackboards? Like, would it help if I pushed them all up? Does anybody care one way or another? Who would like them all pushed up so you can follow the flow better? Who doesn't care? All up? Who doesn't care? Okay. Some of you want them all up. So we can follow the flow. Okay, so how are we going to figure that out? So we know that this vector r is equal to, this is after the rotation, is equal to x prime I prime plus y prime j prime. So we have base vectors, I prime and j prime, that are rotated. And if r beforehand was x reference I plus y reference j, afterwards we just have the same coordinates multiplying new base vectors. So we can also write this as x reference I prime plus y reference j prime. Now what we're trying to figure out is how this can be equal to x times I plus y times j. So we have this great equation, r is equal to r. On the left-hand side, we can put x ref I prime plus y ref j prime is equal to xi plus yj. So now, this is a vector equation. It's a two-dimensional vector equation. These two numbers are known. These unit vectors are all known. So we have two unknowns and two equations, and we can solve these equations for x and y. And that's what we'd like to do. So how can we solve these equations for x and y? If we take this equation here, and we take the dot product of both sides with I, that will pull out x. So we take the dot product of both of the sides with I, we get that, well, I dotted with I on the right-hand side is 1, I dotted with j on the right-hand side is 0, so this just turns into x equals. This gives us an x equals, and on the right-hand side, we have the dot product of this thing with I, so we have x reference multiplied by I prime dotted with I, plus y reference multiplied by j prime dotted with I. Now all we have to figure out is what are these dot products. And we can draw the picture which Pranav advertised to you in lecture last time. And the picture is you draw a unit circle, and on that unit circle you draw the tips of the four vectors I, j, I prime, and j prime. So we can draw a unit circle. And he advertised this last time in the context of polar coordinate vectors. And polar coordinate vectors and these I prime and j prime vectors are very closely related. In fact, they're different versions of the same thing. So here we have I and j. And then we have other vectors. I recommend not drawing this at 45 degrees because then you can get confused about the angles. And here we have the angle theta. So I recommend drawing an angle less than 45 degrees when you draw this picture. Okay, so these are the base vectors. These two are orthogonal to each other, and these two are orthogonal to each other. Any questions about that picture? Now, looking at that picture, we can figure out all of the dot products that we need. For example, I dotted with I prime is the dot product between these two vectors. That's cosine theta. Or I dotted with j prime. That's the dot product of this vector and this one. What we're looking at is the projection of this vector onto this one. And the projection is minus the sine of this angle. And so that's minus sine theta. So look at those two equations and make sure you're comfortable with both of them. Ask me a question if you're not. Okay, so we could fill in more here. So we could fill in j dotted with I prime. And we could fill in j dotted with j prime. And why don't you fill these in yourself, and then I'll fill them in afterwards. So you have 1 minute to do it yourself, and then I'll do it. Okay, j dotted with I prime, we're looking for the sine of the angle between these two, the cosine of the angle between these two vectors, which is the same as the sine between these two vectors. Or another way to say it is we're looking at the projection of this one in this direction, and that just gives this height here, which is this height here, which is the sine of this angle. So this is the sine theta. And this j dotted with j prime is just the cosine of the angle between these two. Okay, now we don't need all 4 of those just now, but all 4 of them are nice to have. Then we can put here cosine theta, and we can put here j prime dotted with I, that was the minus sine theta. So that tells us that x is equal to cosine theta x ref minus sine theta y ref. Similarly, y is equal to, now would you like the exercise of doing this yourself in class, or do you want me to just tell you the answer? All in favor of, I just tell you the answer? All in favor of you do it yourself and see if you can do it? Okay, I just tell you the answer, but the same, we go through the same reasoning and we get here a sine theta x ref plus a cosine theta y ref. Now we can rewrite this in matrix form, and it says that x, y, this list of 2 numbers, is equal to some 4 numbers multiplied by some 2 numbers, x ref and y ref. And we just take these 2 equations, 2 linear equations, and write them in matrix form. And the matrix form looks like this: cosine theta, sine theta, minus sine theta, cosine theta. So this quantity here, we can say that is the coordinates of R expressed in the xy coordinate system. And this quantity here, we can say, is the coordinates of R ref expressed in the xy coordinate system, which are also equal to the coordinates of r expressed in the x prime, y prime coordinate system. So write that down, and I will say it again. Okay, our goal, starting about 10 minutes ago, was to figure out if we know this vector and we know this angle theta, can we find the components of that vector? That was our goal, and the claim is here's the formula. So here are the components of the vector before we rotated it. Here are the components of the vector in the original base system, x, y, after we rotated it. And here's a formula that gets you from one to the other. There are two ways to think about this list of two numbers. One way to think of it is the coordinates of the vector before we rotated it in the original coordinate system. And another way is to think of the coordinates of the vector after we rotated it, but in the new coordinate system. And that's because x prime is equal to x ref and y prime is equal to y ref. This thing here we call R, and that's the rotation matrix. Now I'm going to quickly tell you a different way to think about this same formula. I'm not going to do it so slowly that you can understand it if you're not ready for it. But if you are fresh in your thinking about linear algebra, you might be able to follow what I'm going to say. Always using the coordinate system I and j, these are the components of some new basis vector, I prime. And these two are the components of some other vector, j prime. And this says, beforehand, we know the coordinates of a vector. Before we rotated it was x ref times y ref times j. After we rotated it's x ref times I prime, y ref times j prime. So after you rotate, it's x ref times the first column plus y ref times the second column. And that's just what matrix multiplication does. One way is you look like this to get the formula, but another way to think of it is it's a linear combination of these columns where the weight in the linear combination is given by these two numbers. So the output vector is this first vector multiplied by a unit vector in the I prime direction plus this component multiplied by a unit vector in the j prime direction. So it's a different way to think about it. Even if you didn't follow what I said in detail, you can remember that the columns of this vector are the components of the unit vectors I prime and j prime written in terms of I and j. So this vector here has components cosine theta and sine theta, and this vector here has components minus sine theta and cosine theta. And those are the four numbers you see here. Okay, any questions about this? Now we can do more with this using the ideas of matrix multiplication. And what we can do is, what would happen is we had a bunch of points. Maybe the bunch of points represents the corners on some picture, or all the points of interest in a picture. And we'd like to know what happens to all of those points when we rotate by some angle theta. So we ask the question, what happens to a collection of points when you rotate by theta? Well, the answer is each one gets multiplied by r. Okay, now the confusion starts. If I pull this down and erase it, maybe I should number the blackboards. Then I'm going to pull this one down and erase it. but you can't keep track of the order. Well, anyway, if we do that to a whole set of points, what we can do is we can look at the set of points as a matrix itself. So, for example, over here, I can call one set of points x1, y1, x2, y2, x3, y3, etc. And these would all be the reference values. And each of them will multiply to give this x1, y1, x2, y2, x3, y3, etc. Because this is the nature of matrix multiplication. If I take a matrix and multiply it by a column vector, it gives a column vector. If I take a matrix and multiply it by two column vectors next to each other, it gives me the product of the two like this. That's the way matrix multiplication works. So we can think of a matrix having all the x and y values of points beforehand. So these are the coordinates beforehand. And the rules of matrix multiplication let us multiply this matrix by this vector, this matrix by this vector, this matrix by this vector, and not have to do them over and over again. We just do one matrix multiplication to get all of these output vectors. Now, what can we do with this is we can draw pictures and see this in computer graphics. So I'm now going to show you how to do this on the computer and get pictures and rotate them. So first I'm going to unplug this. Then I'm going to unplug this. Then, according to previous experience, is Luke here? Is that Luke? I can't, my glasses.
Yes, it is.
Okay, now I'm about to crash my computer according to previous experience. And you, as the Mac king, are going to solve the problem. Are you ready? I'm going to plug this in. So far, no crash. Next, please touch screen to begin. Laptop. Send to center display. Turn off lights towards the front, but not too many of them. So far, detect displays. Hey, pretty good. MATLAB, pretty good. Okay, so we are going to go to a meeting in Mud Hall right after class. Okay, so I've got a little program here and I've got a picture here. And what this picture does is what this program does is it draws this picture. So to start with, let's just ignore the rotation part of this thing. So just ignore this block of code here. And what we're going to do is set up the program by clearing everything, clear the figure, display back here that we're starting to run this thing so we can keep track of whether it crashed or not. And then I'm going to draw a picture by defining a reference. I call it x0, a bunch of x and y reference coordinates. And these things draw this picture. So for example, if we look here, we're at 0, 0. That's the origin here. The first corner of this house is at x equals 2, y equals 0. And that's the first column here, x equals 2, y equals 0. Then the next corner is x equals 3, y equals 0. That's the second column. Then I go up to this corner of the house, x is 3, y is 1. Then x is 2, y is 1. That's this one over here. And then I come back to this corner here, and I'm done drawing the box part of the house. Then there's this trick in MATLAB that when you plot a sequence of points, the plotting function looks at this thing here called NaN, which means not a number, and it picks up the pen and says, now I'm going to pick up the pen, and I'm not going to connect the next point to the last one. I'm going to start plotting again. So this uses this thing, not a number. It's a number in MATLAB. Not a number is a particular number, like 0 divided by 0 is not a number. But for plotting purposes, it says I'm not going to plot that point, so I'll start plotting again. And then you draw the corners of this house, which I picked out to be at 3.5. X is equal to 3.5 for this corner. Y is equal to 0.5. That's that corner. Then we go up to the middle of the house. X is equal to 2.5, and Y is equal to 1.5 over here, and so on. And so I've drawn this house. Skip this thing here. Why do we skip this thing here? Because I put in a rotation of theta equals 0, in which case this becomes the identity matrix, and R times this vector, which I made, this matrix I made with 2 rows with X and Y coordinates. We just get that same thing back again. We pull out from that matrix the X and the Y, and we plot it, and this is the plot we get. Now if instead we take this rotation matrix, just the one we derived in lecture, and multiply it by this reference, and then pull out the X and Y, but we put in a different rotation. Let's say we put in pi divided by 4. Then we run this thing, and mine is Command Option R, or you go up to this green arrow and click Run, and then we get this picture rotated like so. And if we want to see what happens in a sequence of experiments, we use hold on. So I can go back and put a 0 here and have hold on, and that means save the plot from the last time. So I'll run it again. The hold on didn't run until after I run it, so now I'll go back to my pi over 4. Let's just do pi over 2 just for variety. And run this again, and I get both plots. Oh, because I do my clear figure at the top. Bad news. Okay. Run it again. I've got my pi over 2. Put in here 0. Run it again. And then I could put here pi and run it again. And I rotate this picture around. And these could represent any pairs of points or any vector which rotates with a rigid object. Any questions about this? Yes?
Can we see 3 pi over 2?
Yes, I would love to show you 3 times pi divided by 2. It's one of my favorite numbers. Okay, bit by bit we could draw a swastika or something. It's getting to be pretty. You can make pretty things like this, right? Now, this isn't fun enough, so what we'd like to do is do this over and over again automatically. So now I'm going to do the same thing again, but I'm going to animate it. So I'm going to take the picture of the house. This is the same picture of the house. I switched programs here. Now I'm going to look at something I'm going to call time, which is going to vary up to 8 pi. And now I'm going to have this block of code, which looks exactly like what we had before, but I'm putting this all inside this for loop. So I'm going to plot, 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 plot. And now I'm going to pick theta to be something that varies from one plot to the next. So I have t varying from 0 to 8 pi. I'm going to pick theta to be sine of t. So the angle is going to oscillate with an angle here of pi. I could pick any number I want here. So the angle is going to oscillate, and I'm going to plot, 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 and then see what I get. So I run this thing and go plot, 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 plot. There you go. Now, you can do this yourself at home, in private or in public. Now, if you wanted to go faster, we could well, I've got this going about as fast as I can, so I can just plot it 100 points instead of 1,000, and I get it to run faster. Or if we don't want it to go so far back and forth in amplitude, we could just put here 1, which is like 60 degrees. And if we want to make it cute, we can do this, we can go hold on. And then we can get sort of conceptual art. Let me go back up here to a bigger angle here like pi. And then we can get some artwork. And if that was too fast, we want to do it slow again, we can go back to our 1,000 points. Now I'd like to do clear figure. I have that, so it'll start from scratch again. Okay. say again, what's being swept out is a circle because it's rotation, right? The tip of all the arrows relative to the base, which is at the origin, is tracking out a circle. And that's a little dense to look at, so we could say, let's not go to 8 pi, let's only go to 1 times pi. What's it do? Is it stuck somewhere? Oh, still running. Command dot in the Mac. Okay, so 1 times this, and let's not do 1,000 points, let's just do like 50 points. And we've only gone up to pi, so let's see what we get for this one. Maybe we want a little bit of a bigger of a pause here, so it happens slower, and we run this thing. And there's our 50 points going around. And you can see this is going in a sine wave. The angle is varying sinusoidally, so it's varying fast here and slow at the end, and the points get very close together at the end as it gets close to the top. So questions about this little program? Of course I will post this. Have I ever not posted something? What did I not post?